If you've ever found a dead spider in the corner of a room, you've probably noticed its legs are always curled up in that same, slightly spooky pose. But this isn't just a random coincidence. It's a clue to one of the most fascinating secrets in the animal kingdom. It turns out every spider is basically a tiny hydraulic machine, and you've just stumbled on what happens when its power goes out. That crumpled up spider is more than just a bit of dust and cobwebs. It's a biological marvel frozen in time. Its posture tells a story, not of a simple death, but of a bizarre and brilliant method of movement that's totally different from our own. We're used to the idea that animals move with muscles pulling bones back and forth. You might even think of something like rigor mortis, where muscles stiffen after death. While that is part of the story, the real reason a spider's legs curl is so much stranger. The truth lies in a fundamental quirk of their anatomy, one that turned them into nature's most surprising little robots. To understand why they end up in this final curled pose, we first have to forget everything we think we know about how to move. Part 1. The missing muscle. To get what's going on with the spider, let's first think about ourselves. Bend your arm at the elbow. Your bicep does the work. Now to straighten it out, your tricep takes over. This is called an antagonistic muscle pair. One muscle pulls and an opposing muscle pulls back. This system is the foundation of movement for almost every limbed animal, from people and dogs to birds and lizards. It's simple, it's effective, and it's how we control our bodies. Now, let's go back to the spider. Here's the wild part. A spider is missing half of that system. In the most important joints for walking and running, spiders only have flexor muscles. Those are the muscles that pull the legs inward toward the body, causing them to curl up. They have the biceps but no triceps. They can pull, but they have no muscles to push their legs back out. This creates a huge biological puzzle. If you can only pull your legs in, how do you ever stretch them out to walk? How does a jumping spider leap 50 times its own body length? For a long time, this was a genuine mystery. The answer isn't in the muscles at all, it's in fluid. The spider evolved a completely different solution, one that looks less like biology and more like heavy machinery. It built a hydraulic press inside its body. Part 2. The hydraulic robot. Every spider is a master of hydraulics, the science of moving things with pressurized liquid. Think of a dump truck lifting its heavy bed. It doesn't use muscles, it uses fluid forced through pipes to create incredible pressure. Spiders figured this out millions of years ago. Instead of blood flowing neatly through veins, spiders are filled with a fluid called hemolymph. This fluid moves nutrients around, but it also has a second powerful job. The spider's main body, where the legs attach, is called the cephalothorax, and it's basically a power pump. When a spider wants to extend its legs, it squeezes powerful muscles in its cephalothorax. This pressurizes the entire chamber, forcing the hemolymph to surge down into its 8 legs. This sudden rush of high-pressure fluid acts like a hydraulic ram, pushing the leg segments straight with incredible speed and force. It's like inflating 8 long, powerful balloons all at once. The pressure can be immense. A spider can generate pressures up to 8 times its resting level for intense activities like jumping. So, a spider's movement is a constant dance between 2 systems. To curl its legs in, it uses its simple flexor muscles. To stretch them out, it fires up its internal hydraulic power plant. It's an incredibly efficient design. By using hydraulics for leg extension, the spider saves space and weight in its legs, which allows its flexor muscles to be even larger and more powerful. It's a masterpiece of biological engineering. But this unique system has one critical, fatal flaw. It only works as long as the power is on. Part 3. The power off moment. So what happens in that final moment when a spider dies? The answer is now beautifully simple. The moment a spider dies, its heart stops beating. The complex muscles in the cephalothorax, the engine of its hydraulic system, shut down. The power goes out. Instantly, the hydraulic pressure that was holding its legs straight drops to 0. The hemolymph is no longer being forced into the limbs. With that outward force gone, the only system left is the default, the flexor muscles. With nothing pushing against them, the flexor muscles do the only thing they can do: they pull. Unopposed, they contract, yanking every segment of the spider's 8 legs inward. The legs collapse into that tight, familiar curl. It's not a choice, just the mechanical result of a system failure. The curled-up position is the spider's natural resting state, the posture its body defaults to when the life-giving pressure is gone. And then comes the final step: rigor mortis. Just like in other animals, a few hours after death, the spider's muscles stiffen up because the energy molecule that lets muscles relax is no longer being produced. For the spider, this means its already contracted flexor muscles get locked in place, cementing that curled pose. So, it's a 1-2 punch. First, the hydraulic system fails, causing the legs to curl. Then rigor mortis locks them into place. It's a perfect, if grim, explanation. But in a twist that sounds like it came from a sci-fi movie, some scientists looked at this dead, curled-up spider and didn't see an end. They saw a beginning. Part 4. The necrobotics bonus. This hydraulic system is so good at gripping and contracting that it seemed like a waste to let it go, even in death. In 2022, a team of mechanical engineers at Rice University had a wild idea. They looked at the curled legs of a dead wolf spider and saw a perfect ready-made gripper. They even coined a new term for their field: necrobotics. The practice of using parts from dead organisms to build new robots. The process is as strange as it is clever. The researchers took a dead spider, inserted a tiny needle into its cephalothorax, the same chamber that once pumped hemolymph, and sealed it in place with glue. Then, instead of fluid, they just puffed a tiny bit of air into the body. The effect was immediate. The air repressurized the dead spider's hydraulic system, and its legs snapped open, just as they did in life. When they released the air pressure, the flexor muscles took over again, and the legs curled inward, grabbing whatever was in their path. They had successfully reactivated the spider's mechanical function, creating a necrobot. And this wasn't just some morbid party trick. The necrobotic gripper worked surprisingly well. It could lift more than 130% of its own body weight and could be opened and closed around 1,000 times before the joints started to wear out from dehydration. Because the spider is made of natural materials, it's perfectly camouflaged for outdoor environments and is completely biodegradable. The potential uses are fascinating. These necrobots could handle delicate tasks like assembling microelectronics or be used in field research to gently collect insect samples without damaging them. It's a stunning example of bio-inspiration where engineers didn't just copy nature, they repurposed it. It's a field that's both unsettling and revolutionary, blurring the lines of what we consider a machine. So the next time you find a curled-up spider, you're not just looking at a dead bug. You're seeing a sophisticated hydraulic machine after a total power failure. You're looking at the ghost of a unique evolutionary strategy, a robot built of flesh and fluid, now switched off. That final pose isn't a sign of struggle, it's a sign of surrender to the very physics that once gave the spider its incredible power. From a simple observation in the corner of a room, we've unraveled a story of missing muscles, hydraulic power, and futuristic robots made from the dead. It's a great reminder that the natural world is full of mind-bending secrets, often hidden in the most common places. The curled-up spider is no longer just creepy, it's a masterclass in biological engineering.